Hello. In the previous videos, we studied linear transformations and matrices of linear transformations. Today, we'll study kernel and range of a linear transformation. We will look at this from point of view of matrices. Okay? So, let me remind you what we learned in matrix topic. For each matrix A, there are some spaces associated to A. The first one, you have the row space. The second one, you have column space. And you have the null space of A. Right? What is the row space? The row space is the space generated by rows of A. Similarly, the column space is the space generated by columns. What is the null space of A? That is all x such that Ax equal to 0. So basically, this is the solution set of the homogeneous system which has A as a coefficient matrix. Make sense? All right. Now we talk about kernel of a linear transformation and the range of a linear transformation. For each A, we have some corresponding linear transformation. Similar to the case of null space of A, we may consider x such that Tx equal to 0. Right? So I write here, we have T. You may consider all x such that Tx equal to 0. Alright? And you may consider all Tx, all vectors of the form Tx. If you look at this, the corresponding space to the null space of A is all x such that image of x is 0 vector right here. So you send a vector from here to the 0 vector right here. Makes sense? And that is called the kernel of T. So basically, that is the null space of the corresponding matrix. Alright, so how about the range of T? Look at this. I already mentioned in here, this is all vectors of the form Tx, right? Where x is in A. So what's that? If we look at this equation, Ax equal to B, right? And you consider all vector B, right? All possible vectors B. So that is of the form Ax. But this system says B is a linear combination of columns of A. So basically, what is that? What is this? That is the space generated by columns of A. Make sense? So this space is corresponding to this guy. Alright? And we call such space the range of T. So basically, in this situation, we have another names. So if you consider a linear transformation T, you have a matrix, a corresponding matrix AT, and the column space of AT is called the range of T, and the null space of A is called the kernel of T. That's it. Agree? So everything you want to do with linear transformation, you just go to work with the corresponding matrix. Agree? All right, let's consider the following example. You have map T from set of matrices of size 2 by 3, 3 by 2 to 2 by 3, okay? Such that TA equal to A transpose. So what is the null space of this? What's the null space? What is the kernel of T? So basically, the kernel of T is what? Is all matrix X in M3 by 2 such that Tx is 0. And this is 0 in M2 by 3, right? But if X transpose is equal to 0, X is 0, right? X is 0. But this 0 is in another space. So basically, the kernel of T has only one vector, which is 0 vector. Make sense? So what is the range of T? So you consider all T's like this, Tx, where X is in M3 by 2. But what is Tx? Tx is X transpose. So if X is in M3 by 2, so X transpose should be in M2 by 3. So what can you say about the range of T? You might think, yes, that is the whole space M2 by 3. In order to show that, you need to do the following step. You need to show that all matrix Y in M2 by 3, for all matrix Y in M by 3, there exists X in M by 3 2 such that Tx equal to Y. But that's trivial. Why? Because by the definition, Tx is equal to X transpose, right? And so that is equal to Y. So if you want to show that, the range is the whole space M2 by 3, you just need to pick X equal to YT. We just show that for any Y in M2 by 3, there exists X in M3 by 2 such that Tx equal to Y. And X is Y transpose. So that means the range of T is the whole space M2 by 3. Now let's consider some linear transformation from R3 to R3 such that Txyz equal to xy and 0. So if you remember, this is orthogonal projection, right? That transform any z right here becomes 0. So basically, you just project the point xyz on the xy plane. Let's find the kernel and the range of T. Okay, so now you can go ahead to write the matrix of T. The matrix AT is equal to 1, 0, 0, 0, 1, 0, and 0, 0, 0. We took coefficients 1, 0, 0 from here, from the definition of T. Makes sense? In the first coordinate, we have only one x, no y, no z. In the second, we have no z, no x, no z, and one y. In the last one, we don't have anything, just 0. Right? All right, so that is the matrix. So you just need to find the null space of A. Let's find the null space of AT, right? So what is that? That is all x such that AX equal to 0. So basically, you need to solve the system of linear equation. So that is 1, 0, 0, 0, 1, 0, 0, 0, 0. And this is 0, 0, 0. Homogeneous system, right? You already have, reduced row echelon form, which is perfect. So basically, you have x equal to y equal to 0. And z is free, right? Z is free. So the solution would be 0, 0, and z, which is z, 0, 0, 1. You see that? So that is the null space. The null space contains all vectors of this form. That's what you have right here, the kernel of T. Agree? And now let's talk about the range. Again, the range of T is the column space of AT. So you just need to find the column space of AT, right? Column space of AT. And look at this. You have two columns like this, right? So basically you can write the column space of A, it is X of the first vector 1 0 0. I write in this form. You can write in the transpose form, plus Y 0 1 0. That is the column space, because these two vectors are already linearly independent. So basically that is X, Y, and 0. Make sense? So that's why you have right here. That is the range of T. So basically that is what? That is the whole XY plane. In this example, we define a linear transformation T from R5 to R4 such that Tx equal to Ax, where A is given like this. Okay, that is 4 by 5 matrix. They ask us to find basics of the kernel space of T. They ask us to find basics of the range and find the nullity, the rank of T. Okay, so let's explain about the nullity of T first, and then the range, and then we go ahead to solve the problem. What is the nullity of T? The nullity of T is the dimension of the kernel space of T. It's just that. That's the dim of what? Of the curve of T, right? So basically, if you remember, this is nothing but the nullity of the matrix A, right? And the rank of T. The rank of T is the dimension of the range of T. That's it. Agree? We already did that in the previous example. But you know, such dimensions have specific names. They are nullity and rank. Okay? So, like previous example, we need to find the reduced row echelon form of the matrix A. I will not solve that in detail. I'll just go ahead to write the reduced row echelon form. Okay? And then using that reduced row echelon form, we will have enough information for this problem. For that matrix, the reduced row echelon form look like this. On this form, you can see that the rank of A is 3, right? The rank of A is 3. So that means the dimension of the rows and column space are 3. And of course, that is the dimension of the range of T. Which is called the rank of T. Agree? So we have answer for the question D. Secondly, we can see the dimension of the null space of A, which is called the nullity of A, right? That is equal to 5 minus 3. Why? Because the matrix A has 5 columns, and we know that the number of columns is equal to the dimension of the column space plus the dimension of the null space of A. So that's why we have this difference, which is 2. And actually, you can see each time when you see the reduced row echelon form of a matrix, you can count, the number of leading elements right here. That is the rank of A, and you count the other one. That should be the dimension of the null space of A. Okay, so once you have nullity of A, that is nullity of the linear transformation. Makes sense? Okay, so we know the nullity of T is 2. Perfect. Now let's talk about the column space of A. From here, we see that the first column, we can pick a basics for the column space, which is the first, the second, and the fourth one, right? But you don't want to put those vectors. You have to pick vectors corresponding to them in the original form of A. So you may pick the first column of A, which is 1, 2, -1, 0. The second one is 2, 1, 0, 0. And the fourth column in A, which is 1, 1, 0, and 2. Right? Why? Because when you do row operations, you change the rows, you change the column space. The row space will not change, but the column space will change. So that's why you cannot pick these vectors, right? At the end, you have to pick the original. Agree? All right, now let's talk about the kernel of T. The kernel of T is nothing but the null space of A. So we need to solve the system AX equal to 0. Okay, but we can see the solution right here already. Look at this. Let me write in this place. So you can have x1 equal to -2x3 plus x5. x2 is equal to x3 plus 2x5. Okay, and then x4 equal to -4x5. And you have two free variables, which is x3 and x5. Okay, if you copy this and write them in the form of solution, right? So you have the following one. -2x3 plus x5, x3 plus 2x5, -4x5. Oh no, here should be x3, -4x5, and then x5, and then transpose. Okay, and now you can separate x3 and x5. You get the following one. First, you get x3, -2, 1, 1, 0, 0, transpose, plus x5, 1, 2, 0, -4, and 1, transpose. So basically these two vectors will form a basics for the null space of A. That means there will be a basics for the kernel of T. Okay? So that's how we can solve such problem. Now let's talk about one-to-one and onto linear transformations. When you study functions, we study bijective functions, injective functions, or surjective functions, right? If you express that using the Venn diagram, so you have a set A, and here's the set B. You have some function f. Function f is said to be one-to-one if you pick different x1 and x2 in A, that will give you different image fx1 and fx2. Makes sense? That is one-to-one. So that means for each x1 you have one y1, right? And if you pick another one, you have different image. Let's say onto if for any y in B there exists an x in A such that f of x equal to y. That means for any y in this set B, you can find pre-image x of y right here. So if a map is one-to-one and onto at the same time, we say Yeah, that is bijective. Bijective map. If f is 1 to 1 and onto at the same time. So what is that? That means for each x right here, you have only one y, right? And for each y, you have only one x. Okay? You know, the second property, the one on onto, right? They say there exists x such that fx equal to y. But there may exist many x for one y. For example, if you consider the map y from R to R plus such that y equal to x squared, right? So this guy is onto. Why? Because if you pick some y greater than or equal to 0, you can find x in R, right? Which is A and this is B, right? So you can find x such that x is just, plus or minus square root of y. So basically in this case, you have 2x corresponding to y, right? But that's still onto. But that is not 1-to-1. Make sense? That is not 1-to-1. Why? Not 1-to-1. Because you have right here, for different number like plus minus 1, you have just one image, y equal to 1. So that's not 1-to-1. And of course, if that is not 1-to-1, that is not a bijective. Make sense? So it depends on how you define that function. Make sense? If you define this function from where? From, let's say, from R to R. This function will not be onto. Not onto, because if you pick some y less than 0, you cannot find a real number x such that x squared equal to y. Make sense? But if you change, you consider y from R plus to R plus. So this is onto, this is 1-to-1. So this is bijective. The onto is already shown previously right here, right? So how to see that? This is 1-to-1. If you pick x1 different to x2, then from here, of course, they are greater than or equal to 0. Then from here, you can see x1 squared should be different to x2 squared. Is it? So that's why this map is 1-to-1, right? So this is very good example. I'm sorry, here should be R plus, not R3. This is very good example to show you about 1-to-1, onto, and bijective maps. So look at this picture. If you consider map from R to R plus, so that means you have the whole thing right here, right? Agree? For each x, you have one y right here, which is good. But, for each level y, you still have another x right here. So that's why that is not 1-to-1, right? Agree? And that is good because, for any y in here bigger than 0, you have corresponding x. You can go back to the x right here. So that is onto. But if you just consider the map from R to R, right? From R to R means from the whole number line x to the whole number line right here. So you might pick some point y in here, right? So such y will not have pre-image via this map. Make sense? But if you just restrict the domain, right? You say, yeah, you just want to consider only x greater than 0 and y greater than 0. So in this situation, the map is bijective because for each x, you have only one y right here. And for each y, you have only one x. Make sense? So that is about bijective, injective, and surjective functions. That idea works in this situation for linear transformation. Agree? So Basically, if you consider a linear transformation T, and T is said to be 1 to 1, if x1 different to x2 gives you T x1 different to T x2. Okay, but look at this. What does mean x is different to x2? That means x1 minus x2 is not 0, right? Then you have T x1 minus x2 is not 0. So basically, if you just compile them together, right? You can write, yeah, the map T is 1 to 1 if any non-zero vector U has non-zero image. Is that correct? So what does it mean? That means the kernel of T has only zero vector. Make sense? So we define one-to-one, right, map linear transformation using this idea. So it turns out that that is equivalent to this condition. We might do this because T is linear. That's why you can just bring T x2, right, to this part, and then you write in this form because T is linear. If T is not linear, there's no way to make that. So you just need to check that the solution set of the homogeneous system of A, right, the null space of AT is just trivial. That's it. Okay, and we have all information about homogeneous system with trivial solution. Okay, let's consider the following example, and you see that. Let's consider A is 1, 2, 0, 0, 1, 1, and 0, 0, 1. It's obvious that the rank of A is what? It's 3, right? Because this matrix is already row echelon form. A has 3 non-zero rows, right? So the rank is 3. A in this case, invertible, because this is square, right? And we know that for such matrix, the null space is just 0. That means the kernel of T is also 0, right? I write T of A, right? T corresponding to A. So if the kernel of T is 0, T is 1 to 1. Makes sense? So if they give you a T, you can find the matrix of T, and then you consider that, okay? Let's consider another example. So we have a not square matrix A equal to 1, 2, 0, 0, 1, and negative 1. Look at this. The rank of A, this case, is 2. It's obvious because this matrix is already row echelon form. And since this matrix has 3 columns, from here we get that the nullity of A is equal to 3 minus 2, which is 1. Of course, that is not 0. And then this is nothing but the nullity of T, right? Of TA. That means, TA is not 1 to 1. Because TA is 1 to 1 if and only if the nullity of TA is 0. Makes sense? Now let's talk about onto linear transformations. You have 2 vector space V and W and some linear transformation from V to W. That sends each x in here to some y in here, right? Equal to tx. So if you write this relation in the form of matrix, so you see that is ATX equal to y, right? And the map T is onto if for any y in W, you can find some x in V such that y equal to AX, right? ATX. So that means any elements in W is a linear combination of columns of A. Make sense? So I can write here any y in W is a linear combination of columns in A. What does it mean? That means W is nothing but the range of T. Means the column space of the matrix A. Make sense? So from here I can write W is nothing but the column space of A. Okay? Or we can do, using the rank, we say, yeah, the rank of T is just equal to the dimension of the column space of A. Okay? So let's consider the following example and then we can finish this section. So if you have matrix A like this, 1, 2, 0, 0, 1, 1, 0, 0, right? You can see from here, this matrix has rank equal to 2, rank of A equal to 2, right? So what is the rank of T? So that is what? That's also the rank of T, right? 2. But the rank of T is 2 less than 3. So in this case, what is W? W is R3, right? And the dimension of R3 is what? Is 3. So the rank of the map T less than 3, that means T is not on 2. Make sense? So that is the way we can test if a linear map is onto or one-to-one. All right, so I think that is enough for today. So now we have right to talk about isomorphism. If you have two vector space V and W, right, and you have some map T from V to W, and this map is one-to-one and onto, right? So in this situation, we say V is isomorphic to W. Okay, so this is really important. We already learned some space like this. Like if we consider R3, so that is isomorphic to the space P2, right? The space of all polynomials less than or with degree less than or equal to 2. Do you remember that? If two vector space are isomorphic, basically you need to learn only one space. The other space is almost the same. And especially in our course, we study finite dimensional vector spaces. Okay, so all finite dimensional vector spaces of the same dimension are isomorphic. And we can look at them as just one space. Agree? All right, so thank you for watching, and we'll see you in the next video. Okay.